Hai, pernah nggak sih kamu pengen punya robot yang punya perasaan kayak di film-film gitu? Sebenarnya sih, bisa nggak sih kita bikin robot yang kayak gitu? Yang bisa punya perasaan sedih, marah, senang, dan sebagainya gitu? Yuk kita tonton video berikut ini.
Hi, my question for MIT is, could you possibly make a robot with feelings?
Hello, MIT. That was a very good question.
Hi, I'm Dr. Goran Gordon. I'm a researcher at the Personal Robots Group in the Media Lab at MIT. We in the Personal Robots Group and in other social robotics group around the world are trying to make robots that physically express emotions in how they move, how they speak, their facial expressions. We can make robots move as if they're happy or sad, but do they really have feelings? In order to really answer this question, we need to think of the following steps. First, we need to define what is emotion, to understand what are emotions. This is a very hard question which science has not fully understood until now. What is it to be happy? What does it mean to be sad? What does it mean to love? Only after we define these emotions verbally, we can move to the next step. And the next step is to formalize this definition in a mathematical manner, to try to make a mathematical model of these feelings. This is also a very non-easy task. To formalize psychological and affective states and processes, not easy. But let's say we answer this question also. The next thing is to program these mathematical models into the robot. And once we program the robot with these mathematical definitions of emotions, then by definition, the robot has emotions. I want to give an example from my own research on curiosity. So I asked the question, can robots be curious? So the first thing, I defined curiosity verbally. So curiosity is the drive to learn as much as possible and the behavior that fulfills that drive. So that's a verbal definition. And then I made a mathematical model about this definition. It ended up with some equations that actually just mean that the robot moves in order to learn. And then I programmed that model into a robot. And the robot moved by itself, discovered its own hand, learned how to reach all by itself. So by these definitions, the robot is curious.
I am becoming a celebrity, alright, guys?
So can we make a robot with feelings? Another thing to consider is that feelings are not necessarily only human feelings. Also animals have feelings. A dog can be happy or sad. And is it the same thing as human feelings? I don't know. Maybe robots can have their own feelings, their own types of feelings. Maybe we can program them to have feelings that are not necessarily human or even animal. The question here boils down to whether we can program robots to behave in an emotional way and how do we perceive them. So to summarize everything I've said until now, in order to actually answer the question, can we make robots with feeling, we must first understand our own feeling, other beings' feeling, and how do we perceive these feelings. After we understand this and define it in a scientific way, we can program it into robots.
So do you think they can have feelings? Bye-bye.
Mesin-mesin itu kalau dilihat rumit juga ya. Terus yang bikin mesin-mesin itu ternyata mesin juga loh. Kira-kira lebih kompleks atau lebih sederhana?
Years ago, James Watt decided that my friend Helga could lift 550 pounds a foot in the air in 1 second. And that's the definition of a horsepower.
This lawnmower has 6 horsepower.
This car has 130 horsepower.
This Cessna has 230 horsepower.
And this jet has 85,000 horsepower. All of these engines produce power by forcing a mixture of fuel and air into a tight space and then burning it.
But they do it in different ways.
A car uses a piston engine. This is a piston engine that's been cut into a half so you can look into it. A mixture of fuel and air enters through these valves into this metal cylinder. It's compressed when the piston pushes up onto it. And then this mixture is burned through a spark plug, causing the mixture to expand, and the piston comes back down. And this happens over and over again. There are multiple pistons in a car, and they're connected through a series of linkages to the wheel, causing them to turn. the piston engine just like in the car, but instead of it being attached to the wheels, it's attached to the propeller.
A small plane like this Cessna actually weighs about the same as most cars, and so it needs about the same amount of horsepower to roll down the runway and get off the ground.
But a Boeing 777, with all its passengers, cargo, and fuel, is about 200 times the weight of the Cessna, so it needs a lot more horsepower.
You could provide that horsepower by using a ton of pistons, but you'd need 67 of the most powerful piston engines ever built to fly a 777 at cruising speed. That won't work.
What you really need is one engine that can produce enough horsepower to fly the plane. A turbine engine is capable of much more horsepower than a piston engine because of the way it uses giant fans to compress the air.
At the front of the turbine engine is an intake fan, which spins and brings a huge amount of air into the front of the engine. As we move backwards through the engine, a series of compressor blades makes that air more and more compressed until we get here. And here fuel is introduced and burned, and that hot, high-pressure flow gets sent out the back of the engine, and that makes the thrust of the engine. But at the same time, that flow passes through a series of 4 or 5 turbine blades, and those blades are connected directly to a shaft at the middle of the engine. That shaft runs all the way back to the front and spins the intake fan. That's what keeps the engine running. We've gone from 1 horsepower to 290,000 horsepower. So Helga, I guess we don't need you anymore. Run free. Join your herd.
Kamu tahu kan masalah terbesar di Jakarta itu apa? Yap, sampah. Daur ulang solusinya. Kamu tahu nggak sih kalau di negara-negara maju sampah itu bisa jadi apa? Yuk kita lihat sama-sama.
Corn husks burn quickly and turn to ash. These lumps burn hot like firewood, longer than charcoal, but are cleaner, greener, and less expensive than both. This is actually made from this, and I'm going to show you how. About 3 billion people in the world use charcoal today to heat their homes and cook their food. But charcoal can be expensive. It produces a lot of smoke when burned, and it's made from wood, which contributes to deforestation. In fact, 98% of Haiti's forests have been cut down for fuel. What we need is an alternative fuel source. Let's take a look at how charcoal is made. We have to first cut down trees for wood, which we then place in a closed vessel and deprive of oxygen. It carbonizes into charcoal instead of burning to ash. We then mix the charcoal with a binding solution and compress that into lumps called briquettes. This process creates a fuel source that works, but has its problems. So let's hack the charcoal production process to make everything about it better. Part of what makes the charcoal production process so expensive is the equipment. Instead of a fancy vessel, you can make a simple kiln out of an oil drum by cutting a large hole in the top and several smaller ones in the bottom. Gather a couple large rocks for the kiln to rest on, a lid for the top, and you have yourself a $15 kiln. We also need some kind of tool to mold the charcoal material from the kiln into briquettes. This is one of D-Lab's earlier designs for the hand press. We pour a mixture of charcoal and binder into the spout here. Hammer down the piston. Slide open the panel at the bottom, and the briquette pops right out. This design costs about $20 to manufacture, but the engineers at D-Lab wanted to do better. They changed the shape of the mold into a square to make it easier to manufacture and significantly cut down on the amount of material used. This time, the mold itself is used to scoop the charcoal. Again, we hammer the piston, and the briquette pops right out. This design is easier to manufacture, it creates briquettes faster, and it only costs about $2 to make. Now that we've made the equipment less expensive, what can we do about making the fuel cleaner? If we can get all the smoke to burn off while the charcoal is being made instead of being used, we can decrease the amount of smoke released in people's homes. Leaving the kiln open for about 5 minutes at the beginning of the process will allow the smoke to burn off outside. So that's why we cut a hole in the top of the oil drum.
Alright, final challenge. What can we do to make this fuel more sustainable? What if we replace the wood with something else? Something like dried corn husks, or dried corn cobs, dried bean stalks, or even dried banana peels. These agricultural waste products, or ag waste, would normally be discarded as trash, but we can use them to make charcoal, and poof, your trash becomes a precious resource. And that's how you turn trash into treasure. Less expensive, cleaner burning, more sustainable treasure.
Kapal laut, kok bisa ya ngapung? Padahal dari besi loh. Kok bisa ya nggak tenggelam?
So if I take this box and just obliterate it in the corner right here, and then put it in the water, the weight of the water rushing in will cause the box to sink. If I take this box and do the same thing, it tips over a little bit, but it still floats. This box uses the same kind of design that naval architects use to prevent ships 1,000 times bigger from sinking. What's so special about this box that prevents it from sinking, even with the big hole in its side? Let's talk about why ships sink in the first place. You probably know that things will float in water if they're less dense than water, and sink if they're more dense. The metal that this ship is made out of is way more dense than water, so you might think it would sink. But that metal is shaped so that it traps a lot of air, which is less dense than water, inside it. So the average density of the hull of the ship is actually much lower than that of water, so the ship floats. But if the hull springs a leak and fills up with water, there's no more air to lower the average density of the hull, so the ship sinks. The design of this box basically prevents too much water from getting into it. This box's hull was divided up into watertight compartments with these walls called bulkheads. So when I made a hole right here, only this compartment filled up with water. The rest stayed dry and were able to keep the box afloat. This box is subdivided, and so is this ship. Say the ship is divided into 10 watertight compartments. If one area of the ship got damaged, only that compartment would flood, but not any of the others. The added weight of the water here would cause the ship to tip over a little, to be angled or trimmed in the water, but it wouldn't completely sink and could still be taken to a port for repairs. So even with subdivision, why do ships still sink? Well, it's impractical and expensive to design an unsinkable ship, especially because most of the time, ships just don't see that much damage. What naval architects do now is try to predict what kind of damage is most likely to happen when designing a ship. Now, ships are more complicated than this box. Naval architects have to think about where to subdivide the ship, the shape of the hull, and equipment that goes into the compartments. We don't know when people first started subdividing ships, but accounts of Chinese trade ships as far back as the 5th century indicate that water would be able to enter the vessel without causing it to sink. It's pretty crazy that technology that existed so long ago is still being used today. Hello, I'm Paul. Thank you for watching Science Out Loud. For more information, please visit our website. See what they have me do?
Kamu dikasih tugas prakarya. Yuk kita sama-sama coba buat robot sederhana. Susah? Enggak juga kok. Yuk kita sama-sama coba lihat video berikut ini. Kamu suka main game? Aku juga. Pernah nggak penasaran caranya bikin game gimana? Atau kamu mau bikin game juga? Yuk kita coba belajar.
Video games are fun to play, but have you ever wanted to make one yourself? How can I make a character run and jump on the screen just by pressing some keys? Just like websites or the apps on your phone, video games are just computer programs. We make them by giving instructions to a computer or to a video game console. And these instructions can be stored in your laptop hard drive or even in a CD-ROM. And are things like make a character appear in the middle of a screen, or when the player hits the up arrow key, make the character jump. When we want to give instructions to another person, we use a human language, like English or Italian. But unfortunately, we cannot speak to a computer the same way, because for now, computers can only understand simple instructions, and they're very picky about the way we word things. In order to give instructions to a computer, we need a programming language. Just like human languages, programming languages can be very different from each other. Many rely on text, so programmers can write words that give instructions to a computer. Let's say I wanted to create a very simple video game where a character moves around the screen. One of the first things I need to tell the computer is that when I hit a certain key, the cat goes up. If I want to use the Python programming language, I could write instructions like this. This language looks foreign, but actually it's not that complicated. For example, here is where I say that whenever the computer detects any key press, if the key is the up arrow key, it needs to move the player, our cat, 0 pixels horizontally and 5 pixels up. To understand the directions I just gave it in Python, the computer translates them into many more simpler instructions. Eventually, these instructions get translated into machine language, whose alphabet is made of zeros and ones. The processor, which is the computer brain, can understand and execute machine language, sending back the right graphics to the screen. Even a simple instruction like move up 5 pixels gets translated into hundreds or thousands of simpler instructions in machine language before the computer can understand and respond. And all this happens in fractions of a second. Other programming languages like Scratch, which is developed here at the MIT Media Lab, are visual programming languages. Instead of using words, in Scratch you can drag and drop blocks together in order to make something happen on the screen. For example, if I want to move a cat around, I would do something like this. So, if I wanted my cat to go up 5 pixels in Scratch, I would snap together 2 blocks like this, and I can do the same with the left, down and right arrow keys. Also, I can play with instructions, and I can say that when I click on the cat, I can change its color, and also I can make him. A game like Space Invaders looks simple, but it's not. It includes player movement, like what we programmed before, but also characters moving by themselves, music and sounds, shooting, collisions, keeping score, and that's where programming gets interesting. Making something move up 5 pixels may not sound very exciting, but basic instructions like this one are the building blocks you can use to create your own video games. What kinds of instructions would you use to create something like a memory game, Tetris, Angry Birds, Minecraft? A professional video game might have millions of instructions written by lots of people all working together to bring the game to life. Human languages have grammar and basic words you can combine together to create things like stories, novels, poems. In the same way, programming languages have grammar and basic instructions you can combine together to create not only video games, but also animations, simulations, and interactive stories. And visual programming languages like Scratch make it easier for anyone to learn how to program. So, instead of just playing video games, now you can make them. So, go make one.
Rumah kamu pernah konslet listriknya, terus mati lampu. Sebenarnya apa sih yang bikin kabel itu bisa terbakar pas konslet? Penasaran nggak? Yuk kita cek video ini.
Let me show you something cool. what just happened here? This power supply created a current, a flow of electrons, traveled over here to a capacitor. Now a capacitor is two metal plates in an insulating oil. Charge can't flow through the oil from one plate to another, so it builds up on one of the plates, charging it negatively. The other plate is left with a positive charge. This creates a potential difference, some voltage across the capacitor. Potential difference is kind of like potential energy. The more charge you build up between the plates, the more voltage you have, and the more energy you have stored in the capacitor. I've been charging this capacitor for about 20 minutes, and it's charged up now to about 3,000 volts. So that energy just sits there until I flip this switch. When I do that, I'm completing a circuit where an iron wire connects the two plates of the capacitor. Imagine destroying the Hoover Dam. Huge water flow. It's the same thing here. Electrons will rush from the negative plate through the iron wire to the positive plate, and the wire can't handle all that current. You might have heard about Ohm's law in physics, V equals IR. Voltage equals current times resistance. Now the voltage in the capacitor after it's been charged up is going to be really high. And the resistance in this wire is really, really small, so the current going through it is going to be huge. When current flows through anything with resistance, even if it's just a little resistance, energy is dissipated in the form of heat. The huge amount of current leads to a huge amount of heat that the wire can't dissipate, so it explodes instead. Now the wire actually explodes before all the charge can finish leaving the capacitor. So I'm going to take this copper bar and touch it to the two capacitor plates so it can finish discharging. Now the thick copper bar has a way higher resistance than the thin iron wire, so it dissipated the energy better and didn't explode.
Kimia itu menyenangkan loh. Kamu bisa bikin hal-hal sederhana dengan kimia. Contohnya dengan hidrogen peroksida. Namanya susah ya. Itu loh yang biasa buat luka-luka. Yuk kita simak videonya.
So this is hydrogen peroxide. You might recognize it from your first aid kit because it's really good at killing germs. But there's more to this guy than cleaning cuts. So this liquid is actually made up of molecules that are constantly wanting to break apart. Hydrogen peroxide, or H2O2, is held together by an unstable bond. This one, between the oxygen atoms. So the molecule wants to break down into smaller, more stable pieces. H2O, or water, and O2, or oxygen gas. Now this breakdown is usually so slow, we can't even see it happening. But what if we did want to see it happen? We can speed up this reaction a lot by using yeast. Yeast makes something called catalase, and what this does is speed up the breakdown of hydrogen peroxide. And something that speeds up a chemical reaction is called a catalyst. And the reason yeast make catalase is because hydrogen peroxide damages cells in DNA. So the catalase goes around and breaks apart hydrogen peroxide so it can't damage the yeast. And actually, our bodies have catalase too to protect our cells in DNA. And the cool thing is, the catalase doesn't get used up at all in the process. So it keeps going around, breaking apart the hydrogen peroxide, quickly releasing oxygen gas and water. And normally this oxygen gas would just get released out into the air, but for fun, we can trap it in soap bubbles. This is the hydrogen peroxide you can buy at the drugstore. It's not very strong, it's only 3%, but this one is 30%. I'm diluting this down with water to 12%, mixing 1 milliliter of dish soap and some food coloring. I'm also taking a gram of yeast and activating it with 4 milliliters of warm water. So what do you think will happen if we mix all these together? So pretty cool, but can we get even more foam? Can we make it faster? Let's tweak each of the ingredients one at a time and figure out how they affect the reaction. Should we change the amount of hydrogen peroxide, the amount of soap, or the amount of yeast?
Tanaman itu sederhana ya, tapi meskipun kelihatan sederhana gitu, sebenarnya tanaman itu kompleks banget loh. Dan intinya, tanaman itu ajaib deh.
Paclitaxel is a compound that can treat cancer. Salicylic acid reduces headaches and fevers. Carotenoids can turn your skin orange, and miraculin changes your sense of taste. What do all of these awesome compounds have in common? They all come from plants! More than 100,000 natural compounds occur in plants, and we've barely explored them. These small molecules are called metabolites. Just like how all of the DNA in an organism forms the genome, all of the metabolites form the metabolome. Even though each metabolite can be made from only 6 elements, there are so many possibilities that it would take scientists thousands of years to make each one and figure out its usefulness. Luckily, plants have already done this for us. Plants have the disadvantage of being rooted to the ground. So, over time, they've trial and errored making lots of compounds to see which ones help them survive and thrive best. And because they've been interacting with other species, like us, for hundreds of thousands of years, some of their chemicals turn out to be really useful, both inside and outside our bodies. But to use plants to their full potential, we have to know what chemicals they make and how they make them. Instead of studying every chemical one by one, what if we could study all of them at once? We could start by mapping the huge network that connects metabolites. In any living organism, molecules are always on the move, being converted and shuttled, decomposed, and built back up again and reused. It's just like a subway system! Except in biology, the people are the chemicals, and the train is the enzyme that converts and moves them. If you look at a city from above, how could you map the whole subway system? Similarly, if we look at a plant, how can we figure out the entire metabolome network? To figure out a path in a system, what we actually need to do is break it. If we mutate or disrupt a pathway and see how the metabolite quantities change, we can figure out the connections between them. Let's say the train from Central to MIT breaks. We wouldn't see students arriving at MIT and would instead see them building up at Central. But not only that, anyone else traveling along the Red Line would also be affected. So it's the redistribution of people which reveals the Red Line subway path and tells us where the train broke. We can use this systems thinking to uncover the plant metabolite network. For example, we know about a compound called cyanopamylate, which protects the plant from UV damage by interacting with UV light, making the plant glow green. But without it, the plant would glow red. So, if we see a red plant, it's like seeing no people at the cyanopamylate station. But we wouldn't yet know where the train broke or what other stations are along the route. To do that, we can mutate a lot of the seeds, plant them, and choose the red ones. Now, we can analyze these samples by using the mass spectrometer. It measures how much of each metabolite is present in the sample. Then, we can use a program to see which compounds were affected and map that part of the network. It's like revealing the red line. Once we figure out how the entire metabolome works, we can use it to engineer plants to create new biomaterials, medicines, and clean energy. We might even discover that plants have the secret to living forever. We just need to unlock their chemical mysteries.